Charging and range. In this video, we'll be covering battery pack charging and methods used to estimate e-bike range, why it matters for correct and safe charger selection, estimating charge times, and estimating range based on pack sizes. Prerequisite VODs, the one on volts, currents and resistance, watts, amp hours and watt hours, electrical circuits, battery cells, cell arrangements, and BMS explained. Charging at a pack level. Here we have a table that shows the various voltages and the corresponding percentages of the state of charge in a battery pack. Note that these can vary depending on specific chemistries and temperatures. The top example is a 10S or 36 volt battery pack running a modern lithium-ion chemistry. In our 10S pack, 42 volts is the full charge, our nominal voltage is around 36 to 37 volts, and flat is 25 to 30. Now you may notice that there's quite a range here between 25 and 30, and that will depend upon the BMS cutoff. Most battery management systems cut off early because there's not a lot of extra capacity to be gained at such a low voltage. And if anything, you're just putting more stress on the battery and therefore reducing its overall cycle life. And then we have the same thing but for a 48 volt pack, which is 13S. 13 series groups. The full charge is 54.6 volts, nominal is 46 to 48, and then flat is 32.5 up to 39 volts, again depending on the BMS cutoff. And then we have the same thing for lithium iron phosphate packs. Remembering back to this specific chemistry, it has a very flat charge and discharge curve. Therefore, the voltage will remain quite consistent throughout its cycle. So, if we know our chemistry and the number of cell groups and series that we have, we then want to be able to select the correct charger. We want a charger that is CCCV. We covered this earlier in the charging of individual cells. Remember, it's just a charging protocol that switches between constant current and then constant voltage. We match the charger output to the cell chemistry and the pack series amount, and then we have to match the connector itself to make sure the battery can plug into the charger. And some systems, usually the OEM ones, require specific brands or protocols for the charger to work. Like this Bosch charger, for example, it has to send a 5 volt signal to the battery management system to be able to activate it to therefore then accept the charge, the full 42 volts from the charger. Here's just a quick reminder of what constant current and constant voltage looks like on the cell level, where the charger is going to dump its maximum amount of current until the voltage gets up to the 4.2 volts per cell, or in the case of a 10S pack, 42 volts. And then it is going to sustain that voltage whilst dropping the current to a point where the current is minimal and then the whole system cuts off, allowing the overall pack voltage to settle a little bit. Charger voltage. So here's a cheat sheet for the chargers. Lithium ion chargers, it's 4.2 volts times the number of cells in series. So for a 36 volt charger, that's 42 volts output. And for a 48 volt charger, that's 54.6 volts output. You do not want a charger that is higher than this because it can damage the battery or trigger a BMS overvoltage cutoff. A charger lower than this, however, will just only partially charge the battery if it's within its charge cycle. For instance, if you had a 36 volt charger and you plugged it into a 48 volt battery, it will only charge barely above empty. For lithium iron phosphate, it is 3.65 volts times the number of cells in series. So for a 36 volt system, you'd be looking at 12S, which is 43.8 volts output. And for a 48 volt system, it'll be 16S, which is 58.4 volts output. Charger current. Most e-bike chargers are within 2 to 6 amps. The more amps, the faster the charging that your battery will have. Current is drawn by the BMS and not pushed by the charger. So the battery management system to charge the battery pack is only going to take as much current as it needs. However, there are other factors that you need to be aware of. For instance, the cell C rating. It's the charge rating of each cell group times the number of cells in a parallel group. For example, if you had 3,500 milliamp hours per cell and you had a 1C charge rate and you had 4 of them in parallel, that means you would have a pack charge rating at the cell level of 14 amps. And then there's things like wires, fuses, and connectors. Are they rated to be able to handle that 14 amps? And then can your charger deliver that 14 amps? And does the BMS have a cutoff that it will allow 14 amps? But to bring it back to the original point, most e-bike chargers are between 2 to 6 amps, so they're pretty gently charged, and depending on the components and the batteries, there's usually a bit of headroom that is built into the pack to allow them to be charged faster. Charge times. A detailed calculation attempt, we'll cover why this is an attempt shortly, is as follows. Let's look at the constant charge section, a lithium-ion pack that has approximately 10 to 80% state of charge, so between this section here. The reason why it starts at 10% is because the battery management system may have a cutoff that shuts down the pack at 3 or 2.8 volts per cell, even though the cells may be able to go down to 2.5 volts per cell, which is not on this graph. We take the battery in watt hours and we times it by 0.7 to give us this charge range, and then we divide that by the charger in watts. So for example, 500 watt hour pack times by 0.7 divided by 42 volts times 2 amps, which is 350 watt hours divided by 84 watts, which is 4.17 hours, and we times that 0.17 by 60 to get minutes to give us an answer of 10 to 80% charge in 4 hours and 11 minutes. Now, the problem with attempting a calculation like that is it assumes all cells are equal. The cell state of health actually gets more complex by the number of cells that you add. Even in the same parallel groups, you can have cells that degrade faster than others and may not have the same capacity. There's also the temperature of the pack, which can affect cell voltage, the battery management system and cell cutoff voltages, which can be different from pack to pack, and efficiency losses in charging due to the heat generated, so the internal resistance of the pack itself, which converts energy into heat. So instead of doing all that complex math, if you're trying to answer the question for a customer, how long does it take to charge, a pretty good ballpark figure is just taking the battery total watt hours, then dividing it by the charger in watts, which gives you hours. Here's a real world example of that. A Bosch 500 watt hour power pack with a Bosch 4 amp charger, approx charging time 500 watt hours divided by 42 volts times 4 amps, or divided by 168 watts, which is the rating for the charger, which is 2.98 hours. Now, this would likely be the minimum time, and it may be a little bit longer if there's things like cell balancing going on. If you want a broad, generic answer, it's usually 4 to 6 hours, but I suggest you at least take the time to do this simple math to give you a bit of an idea, especially as e-bike technology improves, batteries get bigger, and charge times may get faster or slower depending on the quality of charger used. Charger ventilation. Higher power chargers also have a fan inbuilt into them. You want to make sure the ports aren't blocked, and airflow should be up or out to best allow the release of heat from the charger, because we have the fan on one end and the exhaust on the other. We do not want this orientation here, and this orientation would be okay because it's sucking air in from the bottom and releasing hot air out the top. Remember, hot air rises, and if you're trying to exhaust it out here, it's just going to flow back into the charger itself. This charger that is pictured was my old e-scooter charger, and after a good long service life of 5 years, it finally died because unfortunately it was placed in the wrong orientation when it was charging my scooter on a long distance trip. Luckily, I had a backup. Charge lights. On the majority of chargers, a red light means it's charging, whereas a green light means there is no load. No load can mean it's finished charging, or the battery is not plugged in, or the battery is not charging, because there could be a problem with a BMS, fuse, or maybe some wires and connectors. Now that we understand chargers, let's move on to some of the best practices. This is simply just what I do, and I'll give an explanation for each thing because some of it is not conventional wisdom. With a large battery pack like my e-scooter, I tend to keep it topped up between 50 to 100% state of charge. The reason for that is I like to have enough charge in the tank if I need to go somewhere on a long trip at a short notice, and I don't want to mess around with trying to do some advanced charger stuff where I cut off at about 80 or 90%. I'd rather just let the charger do its thing and have the benefits of a BMS performing a balance near the top of a charge. I charge it in a safe place. You want to do this around objects that are non-flammable, of course, just in case you have that 1 in a million incident if things catch fire. If I store a battery pack, I fully charge it and store it above 0 degrees Celsius. Now here's the reasons why. Depending upon your battery pack, You may have a battery management system or other components inside the pack that slowly drain the cells over time. If the battery is left long enough, it may actually cause the battery management system to shut down the charge circuit because a cell group has over discharged. And if the battery is flat, or if a cell group is over discharged and you can't charge the battery, effectively you have a dead battery unless you go in and you do repairs. Now, unfortunately, this is one of the most common mistakes that I see customers make, where they fully drive their battery flat and then they put their bike into storage without charging it, therefore leaving a relatively short window for the battery or cell group to over discharge and then go into a failed state. And also, depending on the battery, if it's your lithium ion or lithium iron phosphate packs, you want to store them above 0 degrees Celsius because you may degrade cycle life below those temperatures. Now, for those two chemistries, at least, you may hear the argument of storing the battery pack at a nominal or lower voltage. This doesn't really matter with modern chemistries because they can handle being at a full charge and stored for a long time. Now, the reason why you do see batteries shipped and stored at a nominal or low voltage, because sometimes there are legal requirements to do so. And at a lower state of charge, if something did go wrong, the battery pack has less potential energy stored. And from a health and safety and insurance point of view, that's good risk mitigation, especially if you're storing hundreds or thousands of batteries in one area. But if that doesn't apply to you, you're welcome to do what I do and just simply fully charge it. And what I suggest, nice typo, is that for customers to charge their battery at least once every 3 months. Now, a battery management system is not going to drain the pack fully in 3 months. However, this is still a good practice because it allows the battery management system to balance the pack at the top end. And if something does go wrong, catching it within a frequent charging interval is a good thing because the battery might still be under warranty. If you leave it for too long and it goes outside of warranty, well, then you may have missed out on the battery being replaced or repaired at little to no cost. Next thing is common sense. If a battery pack has been in an accident or a serious drop, inspect it before using it again. And don't attempt to recharge packs if the battery cells fall below the cell manufacturer's spec base voltage. With most cells, this is usually 2.5 volts per cell group, but it may vary depending on the chemistry. Then finally, don't link packs in parallel or series unless they are designed for it. Estimating range. There's a few factors that we've covered already in this. Cell state of health changes, the unit of watt hours, which is a factor of amp hours times voltage, and then battery management system, cutoff, and balancing. The factors that we've yet to cover are motor and controller efficiency, rider and environment, and the fact that OEMs of e-bikes almost always quote the most optimistic range specs. You might see this language used a lot, like up to 120 kilometers. That's usually taking the most ideal use case scenario when the bike is using its lowest amount of power, which is not realistic for most riders. So, given all of these factors, range is actually impossible to accurately calculate. Therefore, we need to estimate it instead, and to do this, we only need two things: the battery pack capacity in watt hours and the consumption rate in watt hours per kilometer or watt hours per mile. Starting with pack capacity, there's two main ways to measure it. There's the tested capacity, which is ideal, but it can vary depending on the test. For instance, in my example, I do 300 watt continuous tests, but the user may draw more than 300 watts continuous in some scenarios. The more power that you draw from each cell, the more energy that gets wasted as heat, and then therefore the less capacity you get overall. Tested capacity is the watt hours you get between the full charge of the battery pack to the BMS cutoff depending on the test that you use. Otherwise, use design capacity if you don't have the equipment for testing. Design capacity is watt hours, which is the pack amp hours times the pack voltage. Usually there's a 10 to 20% variation between each. Design capacity always assumes more range. In our example here, this battery pack has a design capacity of 614 watt hours and tested capacity of 525 watt hours. So why is tested capacity always lower? Because tested capacity is almost always lower than rated capacity on data sheets at the cell level. Yes, even the high-end manufacturers can be optimistic about their specifications. That's why there's a lot of people out there testing new battery cells. And then there's heat losses, which is all of the energy going through the battery pack and burning off heat from internal resistance. And then there's the level of voltage sag at cutoff. So if you remember back to the battery cells video, we covered things like pulse discharging, where you have a drop in voltage. And if you're using a high power load when the battery pack is almost flat, it'll trigger the BMS to cut off. That's why you see in large EVs like cars, they go into a crawl mode when they're almost flat, so they're not using a lot of power to avoid a large voltage sag to trigger a BMS cutoff. And then we have cell state of health variations. So even in a parallel group within the same battery pack, some cells can degrade faster than others, leading to a slight mismatch in capacity between all of the different cells. And then lastly, obviously the higher load on the battery pack, the less capacity you're going to have overall due to that voltage sag and heat losses. But don't worry, there's a simple formula that you can use. Most consumer e-bikes out there are under 1000 watts and therefore fall within 7.5 to 15 watt hours per kilometer or 12 watt hours to 24 watt hours per mile. If you want to get more specific, here's some useful guidelines from GreenTech, and here's the website here. And here's a screen cap from the section of the website looking at different energy efficiency. But I find personally this is the best catch-all for most use cases. But you might ask, okay, what about over 1000 watts? Well, first of all, like anything, don't rely on the overly optimistic OEM specs. Depending on the hardware, there could be an inbuilt average watt hours per kilometer or watt hours per mile data logging. For instance, on my e-scooter, I have a cycle analyst which can measure all of these things. My e-scooter is 20,000 watts of peak power. It uses an average of 50 watt hours per kilometer. It has a pack that is way too massive at 936 watt hours design capacity. So therefore, it should get around about 187 k's of range at that consumption rate. But I actually got to test this one day. I got 1.3 cycles of charge, so a full charge, drove to the destination, put it on charge, but the charger that I used, that was the one that I mentioned earlier, overheated because I had to stuff it into this little box on this locky dock, and unfortunately I put it upside down, so it stopped working. But I got 1/3 of a charge back. The round trip in total was 220 kilometers, which if you divide it by 1.3, you get about 169 kilometers per charge, which is just a fraction shy of the 187.2. And the reason for this is because the battery pack in the scooter is about 3 years old. It was sourced from about 20 different secondhand e-bike batteries. And despite being the same cells, all of those packs had various different states of health. But luckily, the single cell group low voltage cutoff that turned off the battery only happened around about 1 kilometer away from home, and then it just needed a very long recharge, and then the battery management system to balance things as it was recharging, and now I still use it every day and it's fine. So going back to practical examples, let's estimate the range of this pack. On the low side, tested capacity 525 watt hours divided by 15 watt hours per kilometer is 35 k's, and on the high side it's 70 k's. And if we go off design capacity, it's 41 to 82 k's. And here's where I want you to lock back in, because this stuff is quite important, especially if you're speccing different e-bikes and customers are asking, how far can I get? So the simple way to do this is look at each different battery on each different e-bike, take the watt hours, and then look at our factor of 15 and 7.5 watt hours per kilometer, or 12 and 24 watt hours per mile if you're doing Ks or miles. And I want you to go ahead and work each one of these out. So you can pause the video here and we'll go to the answers shortly. And here we have all the answers in kilometers and miles. But the customer might have a question, why is there such a variation in range? And you can tell them the low side of range is basically assuming that they're going to use the bike in high power, there's going to be a lot of hilly terrain or other factors that lower the efficiency. And the long range is going to be ideal scenarios, flat terrain, no headwind, and all of the factors that go into making a e-bike really efficient. And here's a very useful tool that can put you one step ahead of your competition. Let's say a customer wants to upgrade an e-bike and you're selling them one. This is how you can compare the new and old e-bikes that they might be considering. So you want to ask them, What approximate range per charge did you get on your old e-bike when it was new? If they don't know an answer, you can just default back to this method. Otherwise, if they give you an answer, say as an example 80 kilometers or 50 miles, then all what you need to do to find the customer's self-assessed riding efficiency is find the design capacity of the old e-bike. So for instance, we have an old model of e-bike here, and it has a design capacity of 36 volts times 14 amp hours, which is 504 watt hours. So for the last little bit of battery math, let's work through this one together. We want to solve for the customer's consumption rate in watt hours per kilometer or mile, and then solve the approx range of what they'd get on their new bike. So to start with, we look at their old e-bike. We know it has a 504 watt hour design capacity battery, and they have a self-assessed range of 80 kilometers or 50 miles per charge. So let's figure out their consumption rate. I'll give you a hint. The formula is in the units themselves. So if we take the watt hours and then divide it by kilometers or miles, we get the answer. So 504 divided by 80 gives us 6.3, and then we get 10.08 for miles. So we take this efficiency and we transfer it to the new bike. So now we have the capacity of the battery and the efficiency of the rider, so we can calculate estimated range, which ends up being 127 kilometers or 79 miles. Now there's a few assumptions here, like if the customer was accurate about how much range they got per charge, and assuming that they're going to have the same riding behavior and same efficiency between each bikes. Now just looking at these bikes, they're built for different purposes, so that may not be the case. However, this is still a fantastic method to use, especially if a customer is trying to compare a whole bunch of different bikes, because pegging it into a single consumption rate is a great method to translate what watt hours mean into an actual distance for the customer. Click here to watch the next video. It is the best free thing you can do to tell YouTube to support the channel. Otherwise, if you want to do more, check out the links in the description. Thanks for watching.